Okay, let's dive into this. One of the trickiest parts of programming these days is getting all your different tasks to play nicely together, especially when they all want to use the same thing at the exact same time. So today, we're going to look at a really powerful tool for managing that chaos in iOS, the dispatch semaphore.
So let's kick things off with a question for you. Picture this. You've got a dozen different things happening at once in your app, and they're all trying to write to the same file or update the same variable. What do you think happens? Yeah, it's not pretty.
You get this. A race condition. It's basically pure chaos, where the final result is a total gamble, depending on which task gets there a millisecond faster than another. And this, my friends, leads to corrupted data, totally unpredictable behavior, and a whole lot of app crashes.
So yeah, let's dig into this problem a little more, the race condition. It's exactly what it sounds like. Multiple processes are literally racing each other to the finish line, and without a referee, the result is a total mess. Understanding this is absolutely key to appreciating the solution we're about to get into.
Think of it like a giant crowd trying to cram through a single doorway, all at once. It's a total disaster, right? Some people might get through, others get stuck, and the whole thing becomes completely unstable and unpredictable. Well, in software, that is a recipe for things to go very, very wrong.
So how do we bring order to this madness? Well, we hire a bouncer. And in the world of Apple's Grand Central Dispatch, our bouncer is called a semaphore. And at its heart, it's really just a very, very smart counter that acts as a gatekeeper.
And here's the really cool idea. A semaphore isn't just some clunky on-off switch. It's a smart counter. It lets you control precisely how many threads can get access at any one time. As long as its count is above 0, it lets tasks through, turning that chaotic mob we just talked about into a nice, orderly queue.
And our bouncer, the semaphore, really only has two main moves it uses over and over again. First, it makes a thread wait if the club is full. And second, it listens for a signal that someone has left which frees up a spot. That's pretty much it. Wait and signal.
And this is how it works. It's actually brilliant. When a task wants to access the resource, it calls wait function. This is like walking up to the bouncer and asking, "Hey, can I come in?" If there's room, the bouncer lowers the count by 1 and lets you right in. If not, you gotta wait. Then when your task is all done, it calls signal function. That's you tapping the bouncer on the shoulder and saying, "I'm leaving." The bouncer then increases the count and lets the next person in line enter. Simple as that.
All right, theory is great and all, but let's see how this thing actually looks in practice. We're going to check out a real Swift code example. This is where the whole concept is really going to click for you.
Okay, let's break this code down. What you're looking at here is a super common scenario. We've got a loop that's kicking off 5 different tasks. You can imagine each one is downloading an image or something, and they're all competing for a limited resource. Our job is to use a semaphore to make sure only a couple of them run at the same time.
So the first and most important part is how we set it up. Back in our code, we created our semaphore with a value of 2. What does that mean? Well, that's us telling the bouncer what the maximum capacity of our club is. Only 2 tasks can be running inside our protected code at any given moment. Not 1, not 3, but exactly 2. This number is the key to everything. Now look inside the loop from our code. The very first thing each of our 5 tasks does is call semaphore.wait. This is that "can I come in" moment. So the first task shows up, the count is 2, it gets in, and the count drops to 1. The second task arrives, the count is 1, it gets in, and the count becomes 0. But now, when the third, fourth, and fifth tasks call wait, the count is 0. So they're blocked, waiting patiently in line outside the club. Then, after a task finishes its work, it absolutely has to call semaphore.signal. This is the crucial "hey, I'm leaving now" message to the bouncer. This action increases the semaphore's count from 0 back to 1. And as soon as that happens, the semaphore knows a spot just opened up, and it immediately wakes up the next task in the queue, task number 3, and lets it inside. This orderly process just keeps going until all 5 tasks have had their turn. And listen, this isn't just some abstract programming puzzle. It's incredibly practical. You can use it to limit how many big files your app tries to download at once so you don't crush the user's network, or you could use it to make sure a bunch of background tasks all finish up before you try to update the screen. It's all about controlling access.
But, and this is a big but, with great power comes great responsibility. While semaphores are amazing, there's one critical pitfall you absolutely have to avoid, or you will grind your entire app to a screeching halt.
And that pitfall is called a deadlock. It happens when a task waits for a resource that is never, ever released. This causes it, and maybe other tasks too, to just wait forever. It is the ultimate traffic jam for your code.
A deadlock happens when your logic is flawed. Imagine a task calls wait and gets access, but because of a bug, it never ever calls signal. Well, that task is now occupying a spot forever. The semaphore's count never goes back up, so no other waiting task can ever get in. They're all stuck.
So, the crucial point is this, and it's the golden rule of using semaphores. For every single wait call, you must have a corresponding signal call somewhere down the line. No exceptions. This is how you make sure the bouncer always knows when a spot has been freed up.
At the end of the day, when you use them correctly, dispatch semaphores are a really elegant and powerful way to bring some order to all that concurrent chaos. They give you fine-grained control, turning a potential mess into a predictable, safe, and efficient system.
And that brings us to our final thought. Semaphores are fantastic for managing a pool of limited resources, but they aren't the only tool in the concurrency toolbox. So the question I'll leave you with is this: when might a different approach, maybe a dispatch queue or lock, be an even better choice for the job? Something to think about.